Today we're going to be talking about coplanar waveguides, or CPWs for short. These are a simple type of microwave circuit used to couple microwave devices as well as to make material measurements. They consist of a transmission line thickness S with two gaps with a width of W. The metal sitting on top of the dielectric or the substrate is a superconducting metal, meaning all of these measurements are done in a cryogenic space. Now sometimes the CPW can be designed to be single line transmission, to where the resonator is the transmission line itself. And there you can see on the screen some of the first four modes represented mathematically. And here is a single resonating CPW made with aluminum on top of silicon. You can see the launch pads on either side. Now sometimes CPWs are constructed with multiple resonators coupled to the same transmission line. We call them multiplexed. What you see here is a niobium on silicon CPW with quarter wave resonators multiplexed to the same transmission line. Each of these resonators have a different length, giving a different resonant frequency or standing wave that forms in that cavity. The resonant frequency depends not only on the length of that cavity, but also how fast light travels by that cavity, as given by this equation. This is what a signal looks like from one of these cavities. You can see it's a sharp resonance peak, and then when you get to a lower power, it smears a little bit more and becomes a little bit more uncertain in our measurement. But each of these resonating cavities has a resonant frequency, and associated with that, a quality factor to that resonant frequency. Here is a picture of another signal from a different resonator on a similar device. Here you can see the Lorentzian fit in red, and then also beginnings of the circle fit on the right. This is how we measure the quality factor, which is related to full width half maximum and frequency of resonance. The quality factor can be broken down into parts relating to the geometry of the CPW, as well as the materials used to construct a CPW, both of which are important to report in any type of experiment. Here is a CPW chip. You can see the quarter wave resonators shooting off from the sides. You can also see the main transmission line there in the middle. The little two launch pads there, that's where we connect to our wires in the outside world. Though it's a different device, here's how those wires would connect. These wires had a diameter about 15 micrometers. To fabricate a CPW, one needs to follow a careful recipe in a clean room. To make the niobium on silicon quarter wave resonating CPWs shown in this video, first thing you need to do is take a wafer of silicon. You want to dunk the wafer into a low solution of hydrofluoric acid. This removes the silicon oxide surface layer and gives a much higher quality factor for the resulting circuit. Next, you want to dunk and rinse with deionized water. This is just to ensure there's no acid remaining on the wafer. No harm could come to the facility or yourself. The wafer is usually dunked more than once in different baths of deionized water. Once the wafer is properly deoxidized, it's now time to deposit the metal. This is done through a sputtering gun in a physical vapor deposition chamber. On the video you can see a sputtering gun in a glass chamber, similar to how we would deposit this onto our wafer. This is done 1 nanometer at a time until we have our total thickness of about 200 nanometers. Now that we have a uniform plane of metal on top of our wafer, we need a way to design a circuit pattern on top of it. To do this, we need to first spin resist. This sappy polymer resist protects the parts of the circuit in the metal that we do not want etched away. And by spinning our wafer high speed with a resist dropped on top, we create a uniform coating. We then expose the wafer under a UV light with a mask being placed on top. This mask will have the design of our circuit, and its design will be printed onto the resist. We then place this wafer into a developer, just like how you would a photograph to make the picture come out clearer. And then we place this entire wafer into a reactive ion etch, where a plasma SF6 will eat away at the parts of the metal that are not protected by resist, leaving exposed silicon trenches where resist did not cover. Wash the remaining resist off the wafer with an acetone and an isopropyl bath. And then you can dice the wafer to get your individual chips. In the video, you see one of these chips, a niobium on silicon coplanar waveguide with half the resonators covered. Besides the new material deposited on top, this resonator design is exactly what I showed you before. And you can use this resonator design to determine what the dielectric constant of this newly deposited material is, or at least what it is as this thin film on top. The CPW can be modeled as a superconducting circuit sitting on top of a substrate H1, in this case silicon, with the material H2 being the effective dielectric contributor on top. As you can see with this diagram, by adding the material, the effective resonance frequency of the resonating cavity is shifted. This is because essentially the speed of light, or the effective dielectric of the circuit is changed, causing a resonant frequency shift. It's through this resonant frequency shift that we can determine the new effective dielectric of this material through these equations. The effective dielectric is given above, where Q1 and Q2 are the filling factors, or how much energy is located in each dielectric source, whether it be the material on top or the silicon on bottom.